A single hidden layer feed-forward neural network with a nonlinear activation function and an infinite number of neurons is a universal approximator, meaning that in principle it can represent any continuous target function. The reason they haven't cured cancer though, or solved the Schrödinger equation, is because there's no training algorithm in the world that can reliably find those representations in the astronomically large, unstructured hypothesis space that they inhabit. One of the many approaches to constraining the hypothesis space in model design is to hard-bake latent structure into their architectures, directly encoding known symmetries and compositional rules, so that the model can learn by optimizing parameters within a well-defined function class, rather than being forced to rediscover this latent structure from data. This talk is about a very simple example of adding latent structure to neural networks in the form of physical symmetries. If I have a molecule, that molecule really doesn't care where I put my x, y, and z axes. And yet, the numbers that I might use to represent where the atoms are in that molecule do depend on where the axes are. But your neural network just has no way to know that that can't possibly affect the physics. In this mini-series, I've carved out what I think is the simplest possible route to baking physical symmetries into neural networks using equivariant convolutions. I'll start with vanilla convolutional neural networks, and we'll work our way through to doing convolutions on stacks of tensor fields in 3 dimensions that respect physical symmetries. Put another way, this talk is basically about understanding equation 3 of the Tensor Field Networks paper, which was the first clean and explicit framework for building neural networks with equivariant convolutions, and which has given rise to many of the modern approaches in deep learning in physics and chemistry with architectures like Mace, Allegro, NetQuip, and others. I do this by focusing mainly on the 2-dimensional case, that is to say SO2 symmetries, because the algebra is really very simple and they're very easy to visualize. And once you've got familiarity with the SO2 case, the leap to 3 dimensions at the end feels pretty trivial. All the usual provisos about notation choices and possible mistakes apply, so I hope you enjoy it. Thanks.